And that's odd. Okay, we'll probably do a metric review also, but we probably won't be able to do that till next time. Remind me later. Okay. All right, so what we're going to do is just, I want to keep it up, so if there are any questions, people can ask questions. I can see that. So the prologue is about the nature of science. And one thing is that also some people, so before we start that, because I make the PowerPoints available, sometimes people like to take notes, of course, and that's a good thing. Especially if I'm doing a homework problem or something, you'll want to take notes because that'll probably be on the test. I wouldn't be bothering to do it in class if it wasn't going to be something important. And if it's important, then it's probably on the test. So anyway, so you'll want to make notes. Now, sometimes people want to have something that refers back to the PowerPoints too. And so you can print off the PowerPoints. So if you go to Home and print on the PowerPoints, then there are different ways of printing them. I mean, you don't want to print one page per slide, which is what this would do. You can print selections, okay? You can also print different sizes of slides. So there's this thing where there are 3 slides, and so you've got the slides, and then you can make notes, okay? However, some of my PowerPoints are pretty long, so that still would take up a fair amount of paper in your printer. I don't know if you can just save it this way to make notes. Of course, you can make notes on the bottom of the PowerPoint too. Some people know how to do that. You can also, some people print them out, you know, so you might have 6 slides like this. And that leaves a little bit of room for notes. You can also do what's on here. It says scale to fit paper. So if you're watching carefully, you'll see that they will get a little bit larger in that case. Okay, and you can play with the margins and things too to make them look larger. But some people like to do that, so they print them out and then they have a page of notes. I've actually seen people take them and cut out, so they print them out and tape those into their notebook so they can make notes around it, which was a really great system from what I saw. You can even make them smaller, okay? So, and you can do horizontal or vertical. Vertical just means that it goes 1, 2, 3, 4, 5, 6. That's horizontal actually. If you go to like vertical, then it goes 1, 2, 3. So you're going down the column, which hardly anybody wants to do. But you can print out smaller ones. You can change the paper. So if you're printing out 9 of them, usually what you want to do is change the paper to the landscape so that they fit better, and then you get larger ones. And again, you can do that. Scale to fit paper is already on, so that's as large as it can get pretty much right now. Anyway, so some people like to print it out small and then have them available to look at. Okay, so anyway, and you can also, of course, print them in black and white or grayscale. There's also a outline. Now, if you do outline, basically what it does is it takes out all the pictures. Unfortunately, it takes out some of the words because if I put the words in as a text addition, it eliminates those, unfortunately, too. But sometimes people do that. It doesn't really save that much room on the piece of paper, although, of course, you would want to make their paper back to portrait in this case. But anyway, that's a possibility too. So anyway, I'm just saying that since you've got the PowerPoints available, you might want to take advantage of that. And you can also add notes down here, right? There we go. So you can also add notes down below, but it's hard to do an equation that way. The other thing is that what I will be doing is drawing on the PowerPoints too. So so a lot of times the PowerPoints now will have blanks in them for me to do problems, whereas I used to do them on the board. And so that means you can draw on them too. And so you can do what I do, except I am fortunate in having a touch screen computer. So I've got a desktop one, but it's still a touch screen. So anyway, so I can, you know, draw on here. Okay. So anyway, yeah, it's a horrible. Happy faces look really weird till you put them in a circle. If you don't have the circle there, it looks a little odd. Anyway, so you can draw, and happy faces, by the way, were invented. They actually were invented by the 70s by a farmer in Michigan, I believe, who did them on his barn or something. And so a happy face is actually an invention. Anyway, so yeah, so there we go. Okay, all right. So anyway, so prologue. What we're going to be covering is a brief history of advances in science, scientific methods, the scientific attitude, science, art, and religion, and technology. Okay, so the idea is that I've got two contrasting pictures here. This is like the old days. This is like the new days. And right now, this is getting more and more relevant. Of course, we don't really have giant test tubes usually wandering around our cities. But with the coronavirus, science is definitely entering our lives in a huge way. And but people used to work often alone. They kept the discoveries that they made a secret. So we have our old alchemist here. Was he going to share his knowledge? He was trying to find maybe how to make gold. Did he share that knowledge? He may not have, because he was trying to make gold. It was for money. And if you were, you know, the maker of a better sword, you might keep that secret or share only with your clan or your guild. So information was not shared through the world like it is now. Scientific knowledge is freely available to the world. And so anyway, that's actually one of the things that advanced science. Anyway, so we're going to be talking about how science has been advancing and how it's made a difference in our lives, so that now we have lots of shiny things and light to see them by. And it's made a huge difference. I, for instance, would be dead about 4 times by now. I would have been dead the day I was born if I hadn't gotten a blood transfusion, and dead several times since then. And so most of us actually, usually I have the whole class, I have people raise their hand if they would have been dead by now. And usually it's about 30% of the class, and which is what used to happen. People used to die in childhood. And of course, there were all the diseases that were running around. And if you got a splinter in your foot, you could die of blood poisoning. Most of us don't worry about that at all anymore. We know if our foot gets injured, then we can put an antibiotic cream on it that will actually work. Instead of smearing it with cow manure or something, honey actually is an antibiotic, so that one might have worked. But, you know, we know what will actually work. And so we don't die of so many things that we died of before. And I had my appendix out, you know, could have died from that. People did used to die from that. So the thing is that, yeah, we have made huge advances. And that's one reason we have so many people in the world, is we have saved so many lives through science. Okay, so we're going to be looking at a couple of scientists. And over the course of the book. And some of the scientists we're going to meet up with Aristotle, Archimedes, Galileo. Now, Aristotle was very early, and Aristotle is not a good scientist in that he didn't do experiments, okay? But Galileo was the first true scientist, the one who did experiments and published his work to the world. and rigorously did experiments. And so Galileo is really considered the first true scientist in many ways. And we'll talk about Archimedes, and a great mathematician and experimenter and inventor. And we're going to talk about Robert Boyle and Isaac Newton and Antoine Lavoisier. Those are some of the scientists we're going to meet up with. So Galileo laid down really the rules for science as we know them, for physics and stuff. And Robert Boyle started to tell people in chemistry, how they needed to do it by taking careful measurements and writing everything down, okay? And then Isaac Newton came along and had more scientific laws than anybody else. And then Antoine Lavoisier completed the rules for chemistry. And so these were 4 very important scientists, Galileo through Lavoisier, who were setting up early science so that we have our scientific revolution. And we've gone from working alone and keeping secrets to sharing knowledge with the world and these huge advances. Okay, so that's what this page is. It's just pictures and words. Okay, all right, so let's talk about the scientific method, because that is what makes it all possible. Now, scientists don't always follow all these steps completely, exactly, but the idea is that this is a general sort of rule. I mean, first of all, you have to have a puzzle that you want to solve usually. So there's some unexplained fact. Maybe you want to know why the sky is blue. By the time you finish this class, you will know why the sky is blue. But maybe you don't know why the sky is blue right now. And why is it blue on this planet, but it's red on Mars? Okay. So there are questions that can have additional questions added on to them. So what you can do is make an educated guess. That's what a hypothesis is. A hypothesis is your first answer, an explanation. And so one of the things is that a scientific hypothesis must be testable. Uh-oh. Sorry, I picked the wrong set. Okay, goodbye to you. This is the one with blanks in it. We don't want the one with blanks. Oh, that's the print one. Yeah. So it used to be I had print ones. I really need to get rid of those. Okay, where's my Prologue and not print one? Where did it go to? Oh, it's way down there for some reason. Okay, same thing, just doesn't have blanks. Okay, so where were we? Here we were. Oh, look at that. Testable. Okay, so anyway, so a scientific hypothesis must be testable. And so testable means that you could run experiments. So what you do is you sort of predict consequences of the hypothesis. So let's say you want to know what the sky, why it's blue, and you say maybe it has to do with oxygen. Maybe oxygen is blue. You know there's oxygen in the air. That's an educated guess. You're using your best knowledge. You know there are oxygen atoms in the air. Maybe oxygen atoms are blue. And maybe Mars doesn't have blue skies because it doesn't have a lot of oxygen. See? I'm thinking about it here. Okay, so that's sort of the consequences of the hypothesis. Is you're thinking, well, if there isn't as much oxygen, would the sky not be as blue? And like if you had more oxygen, would it be bluer? So you could say, okay, maybe I can test that in the lab. Maybe I can have a box of air that has only a little oxygen and a box that has a lot of oxygen. Maybe I can detect if there's a difference in the blueness. So you could predict consequences, right? You could think, okay, well, what if I go way up high in the mountains where the oxygen level is low? So I'm on Mount Everest. Is the sky less blue? So you can think about, what are some tests that you could do? So you predict consequences, and then you perform experiments. Now, so you might go to Mount Everest and say, okay, let's measure the blueness of the sky. More blue, less blue. Okay, in the lab, you might test it out. You might say, okay, well, let's check some of the other contents of the atmosphere. So the atmosphere has nitrogen in it, it has oxygen, and those make up most of the atmosphere. Then there's a little bit of argon, maybe it's the argon. So you would make tests and make some experiments. or sometimes you have to make calculations, because some things you can't really do in a lab, or you can't do totally in the lab. So, so for instance, like black holes, we don't have a way to put a black hole in a lab, but we can test gravitational things, because a black hole is the way it is because of gravity. Some of those tests can be done in the lab, or are experiments we can take place on Earth, but we can't do a whole black hole experiment because we can't make one, and they might be a little dangerous in the lab. So sometimes we have to do a lot of calculations. And in fact, my husband, who's sitting, sometimes you'll hear his voice. So he's sitting in the other, I'm in what used to be the dining room. He is sitting in what used to be the living room. Anyway, so we're both at home yelling over our computers. Anyway, so he does a lot of calculations. He's a physicist who does calculations for Fermilab, which is about all these particles. And they do a lot of calculations, and then they run an experiment and see if the calculations come out the same as the experiment, because then you know you're on the right track. Okay, so you can do calculations and then check data in the world. Anyway, so you do the experiments, and then finally you come up with hopefully a general rule that helps you to understand why the sky is blue, but maybe why also the sky is red on Mars, or, you know, actually it turns out it's a little bit blue on Pluto. So anyway, so what is the reason the sky is blue? Well, it has to do with scattering of the wavelengths of light. And the smaller wavelengths of light are scattered by the molecules in the air and by the atoms. And so the blue is a smaller wavelength of light. And so that's the one that gets scattered, that we see the most of. Violet gets scattered too. But blue is the one we see the most of. So that's why our sky is blue. And so anyway, and our atmosphere is clear enough that we can see the blue color. Whereas on Mars, what happens is there's a lot of carbon dioxide in the air, much more than oxygen. And so what happens there is the air tends to be more reddish colored. Okay, so we get a general rule about molecules, that molecules will scatter wavelengths of light, and that has to do with the size of the wavelength, and that's why we have a blue sky. Okay, so anyway, so you try to put it all together in a sort of more general rule. So it's not just what's happening here on Earth, but what's happening in all of the universe. Okay, so let's look at scientific hypothesis. Remember that it's an educated guess, okay? It also has to be tested, and it has to be an explanation. Okay, so here are 4 statements, but are they scientific hypotheses? So, number 1, physics is the greatest science. That would probably be classified as an opinion. So even though I may think it's true that physics is the greatest science, that's not a hypothesis. Okay, so no, because it's more of an opinion. Because how do you define greatest, right? And also it's not an explanation of anything. Okay, so let's look at number 2. Leaves turn red in the fall because they have an iron shortage. Okay, that could be a scientific hypothesis, right? So it could be a scientific hypothesis because it's something that we can test. Now, as it turns out, that is not why leaves turn red in the fall. So that's okay. Hypothesis can be wrong. That's the point. You try it out, you test it, and if it's wrong, then you've just built up some knowledge. You found out what is not true. And in science, we do a lot of what is not true so that we're leading towards the actual truth. So we chip away all the things that are not true. Anyway, so having an iron shortage would be kind of silly because iron often turns things red. So actually maybe having too much iron would be a reasonable explanation, but that's not true exactly either. The reason that leaves turn red in the fall is if you look at this picture down here, this is just the skeleton of the leaf when the fleshy part has been etched away. The skeletons underneath are red colored for maple leaves, especially. And the thing is, what happens in the fall is the reason leaves are green is because they have chlorophyll molecules in them. And the chlorophyll molecules absorb red and blue light, but they reject the green light. So we see the leaf is green because of all the green light that is being reflected off it. And so anyway, but once the chlorophylls, what happens in the fall is the tree will either stop making chlorophyll because it knows the leaves, it's going to get frozen soon, or it sucks the chlorophyll back into the bark to reuse later in next spring. And so what happens is that the leaves then no longer reflect the green away, and you can see a little bit of the true color underneath, which is more of the red. Okay, so anyway, so yes, that could be a scientific hypothesis. It could be tested and found wrong or incorrect. Okay, what about black holes are filled with an undetectable substance? Well, that's got a lot wrong with it. For one thing, it's really hard to test something that's undetectable. And it's not really an explanation of anything. It's not saying how this affects anything, so it's not a very good explanation. Anyway, the thing is that would probably not be considered a very good scientific hypothesis. Now, having said that, there are actually hypotheses about things called dark energy and dark matter, which are things that we cannot see or detect very well. They don't give off light. So they're called dark energy and dark matter. And so we have to detect them using other methods, like trying to detect their effect of gravity. But they don't give off light. So it's almost undetectable. Okay, so we do have problems like that in physics. Okay, now, 4, we were put on Earth to find happiness. Well, that's not a very good scientific hypothesis, right? That is more of a philosophy of life. And so it's a cool idea, and it would be nice if it was true, but it's not scientific. Now, that's a hypothesis, okay? So a explanation that you can test. A theory is a word that people use often when they really mean hypothesis. Hypothesis is such an awkward word. So what they use instead is the word theory. They'll say, I've got a theory about this. Okay. You know, why are Sam and Marta getting a divorce? I think I know. I've got a theory. That's not, though, in science. A theory is something that has been tested many times. So if we were trying to find out why the sky is blue and we tested many times and we had a really good idea, then it might become a theory. So anyway, so when people say theory casually, that's not the same thing as a scientific theory. So when you see something like atomic theory or theory of relativity, that doesn't mean it's just an idea. It's not just a hypothesis that's still being tested, especially. It's something that's been tested and has not been found false many, many times. So things don't get to be theories unless they've been tested a lot. So like the atomic theory, the idea that everything is made up of atoms pretty much, right? We're pretty good on that. Most of us are pretty sure that when we knock on wood, we know there are atoms in there. When we breathe in air, we know there's atoms in our air. So most of us are okay with that one. Theory of relativity, it's crazy, but yeah, that one was proved about 15 years after Einstein proposed it. And so we'll talk more about that hopefully a little bit later. So they are tested, they're verified hypotheses. Okay, now one that people have a lot of trouble with, theory of evolution. Again, people tend to think theory just means an idea, and it's not. It's been tested a lot. And the theory of evolution is so simple, the idea that creatures change because the ones that survive carry on the genetic code, and the ones that don't survive environmental pressures, well, they don't have kids, right? So now that we know more about genes, you can see how things adapt over time due to environmental pressures. And so Darwin didn't know about genetics, okay? There was no gene theory in his days, or gene ideas. And so anyway, so yeah, but theory doesn't mean something that's easy to just dismiss because it has been shown to be true many times. Now, over the years, theories may undergo change and refinement. So like I said, Darwin didn't know about genes. Now that we do know about genes, we can understand a lot better how it is that animals change their genes over times and evolve into strange and wondrous creatures. One of the natural experiments that happened accidentally, because people have been breeding animals for years, for hundreds and hundreds and thousands of years, to get all of our different varieties of dogs and stuff. We've been doing that a long time. Anyway, so one of the accidental experiments had to do with something called the peppered moth. The pepper moth was a moth that lives in England. And most of the time, about 90% of them are this gray color more, and maybe 5 to 10% of them are this black color. And the thing is that on the tree bark, usually the gray one matches the tree bark. So here's the gray one here, and you can see how it matches the tree bark very well, whereas the black one kind of stands out on these light birch trees. And so what would happen is usually the black ones get picked off by birds during the daytime, okay, whereas the gray ones were hidden, okay, so there would be more gray ones than there were black ones. Well, what happened was that England was heating by coal. So the Industrial Revolution started up, and what happened was the coal dust was everywhere, and nasty, nasty coal stuff was falling out of the sky, and it was coating the homes, and it was coating the trees. So the trees got turned darker. And what happened was that once the trees turned dark, then the gray moths showed up better, and they got picked off by the birds, and soon more than 90% of the moths were the dark color. So environmental pressures, the birds were, and the coal dust were driving the gray ones towards extinction, and the black ones became the dominant form of the moth. But then what happened? Well, they stopped using. They put scrubbers in the coal stacks. People started using natural gas at home. And what happened was the skies washed the coal dust eventually off the trees. The trees turned gray again. And then the black moths got picked off. And the only ones that were surviving were the gray moths. And so the gray moths came back into being the dominant form again. So it was an accidental experiment that occurred around 100 years ago. Okay. Now, a deliberate genetic experiment has to do with foxes and tameness, because it turns out that taming animals, a tame animal, is different than the animal usually in its wild form. And so dogs, especially, are very tame. In fact, they think people and dogs, there's all sorts of wonderful and interesting stuff coming out about people and dogs and how long they've been what's called domesticated. And that it probably started out, thousands and thousands of years ago when the dogs' ancestors started hanging out around the campfires because we had the food. And they started, we started feeding them also. They started hanging out with us. And soon they learned that looking really cute helped. And so they became more cute. And they actually found out that dogs have more expressive faces. They have eyebrows, which the wild dogs and wolves do not have. More eyebrows that can move more, because the dogs need to give us that really sad look that makes us give them treats, which my dog, Leo, is an expert at this, of course. He's got that chow. He's chow and golden retriever, and he just can have the saddest look, of course. Anyway, so the dogs are not at all probably what their wild ancestors were like. It's so much difference. So they decided to see, though, if they could tame foxes, because there are only about 5 or 6. That can't be right. There aren't that many animals that are actually considered domesticated and tamed. There are cattle, there's sheep, and pigs, and dogs, and horses. Okay, those have been domesticated and they can live with humans, but then they're wild animals and they're different. So anyway, so tame foxes, they decided to see if they could make foxes love humans. So what they did was they started out, it was a fox fur farm to support the research, and they would come up to the baby foxes, the kits that had been born, and they would, if humans would come up, and if the baby foxes snarled and spat at them, well, then those were destined to become fur coats. The ones that were more accepting of the humans, those would go on to breed again. And so 45 years, now about 50 years of breeding, and they have tame foxes. So they've just been taking the ones that were nice to humans over all these years. And they ended up with these little cuties here. And they found out that what happened was that it wasn't just their tameness. When the foxes got tame, other things changed too. Their eyes often became more rounded. Their tails could get curly. They ended up having spots. So it wasn't just the gene for tameness. In fact, what it turned out to be was that now that we know about chromosomes and stuff, we know that some genes are on the same chromosome and they're linked with other genes. And it turns out that the gene that makes animals domesticatable usually is their fight or flight gene is faulty. So they don't know to flee. They stick around. And so anyway, but that faulty gene is connected to one that also makes the cartilage faulty. And the cartilage is what shapes your eye sockets and your ears and your tail, if you had one. And so it would make ears more floppy often. Okay, so dogs have more floppy ears. And so it turns out that those were connected. So as an animal became tame, it also emphasized this cartilage issue, and that's why the tail would curl and why the eye sockets would get bigger. So anyway, so yeah, so this is the idea, is that over the years, as we learn more about genetics, we can change and refine the theory of evolution. Okay, or the theory of relativity or the atomic theory. Things can change a little bit, but that doesn't mean it's been disproved. It just means we can refine it. We know more. Okay, so we've covered hypothesis, we've covered theory, and it's 11:25. Okay, and the other one that we need to know is the scientific law. So what's a law? A law is a concise statement that describes a fundamental relationship in nature. So laws are just describing a relationship. They are not explaining it. Okay, so hypothesis and a theory are more explanations. Okay, a law doesn't have to explain it. So like I was saying, Newton has more laws than anybody else. He was a great observer of things in nature. He couldn't yet explain them, but he certainly saw them. Okay. So anyway, so the law of conservation of mass was one of the contributions of Antoine Lavoisier. And the thing is that he saw that during a chemical reaction, there was no gain or loss of mass. And we'll talk more about that when we do the chemistry part. But of course, that's very important. And we understand that now because we know a chemical reaction is just atoms rearranging themselves into different molecules. And so Antoine Lavoisier, he observed that mass should not change. So a law states the finding, but it doesn't explain it. He didn't know really about atoms yet. Okay, but he did realize that the mass should not change. Okay, so having the right attitude is really important to science. The idea is that you should be curious, of course. You should do experiments. And then there's openness and communication, because that's one of the biggest things about science is that we share that knowledge. Okay, we're open and we communicate. Okay, and then there's humbleness, which is a willingness to admit error, because sometimes people are wrong. They have a hypothesis, they test it, it's wrong. And the thing is, sometimes it's very hard for people to give up that idea. So you really have to work on that humbleness to say, yeah, maybe my hypothesis isn't a good answer. And so anyway, so I've seen some great examples of this over the years. Because some uncertainty is okay. You know, you have a hypothesis, it doesn't work out, you're supposed to try again. Once there was an experiment where there were some rats that naturally get cancer. and they've been bred so that you can buy rats, and they're all the same genetically. They all get cancer. So anyway, so some cancer researchers were trying to see if they could cure the cancer, and they were giving them some injections, and they were showing some pretty good results. So they published their information to the world. And the thing about science is other scientists are supposed to be able to repeat your experiment and come up with the same answers. And so they tried to say everything about the experiment. And that's why when you usually did laboratories in high school, sometimes they would have you do a purpose and a procedure. What was that about? Well, the procedure was there so that someone else could repeat the experiment. So you're supposed to tell everything about the experiment so someone else can do it. And so anyway, so they did that. They wrote everything about their experiment so that the other people could repeat it. So some group decided to redo the experiment. And so they bought the same rats. They got the same medicine, and they followed the same schedule, and they fed them the same food, and the rats. And unfortunately, their rats were still dying of cancer. So they went to the other scientists and they said, hey, what's going on here? And so they started to go over all their work to see what was different. Why was one group of rats healthy and the other group of rats dying? And they found out only one tiny little difference, which is that in the first laboratory, the lights had been turned off at night. And in the second laboratory, the lights had been left on at night. And so maybe that extra stress was causing the rats to get the to not recover from the cancer, or maybe it had to do with the rats often are white and they often have very thin skin, so the light coming through might actually have been affecting the medicines. I forget what the answer was now, but the idea is that those two got together, the two groups, and they figured out what it was, this very tiny difference. Okay, so anyway, so humbleness, willingness to admit error, willingness to get together and work through these things. That's so important to the scientific progress. Okay, so anyway, so science certainly has limits. So science is studying the natural world, and we explore it with our five senses and their mechanical extensions. So we have eyes that can see, but we have telescopes that can see further. And we have devices that can detect infrared and ultraviolet and other light that we can't see on our own. And the word supernatural means above nature. Okay, so super means above nature. Okay, and finally, science, art, and religion are ways that we look for deeper understandings around us. And they're all good things for you to explore. A philosophy of life is very important. For instance, right now, today, we are getting a new president. And knowing what a good man is pretty important sometimes. And being able to look for truth instead of listening to lies is terribly important still in our world. So having a philosophy of life is extremely important. And science, of course, explores the physical phenomena of the world. We're looking for the laws of nature. Scientists believe there are laws. Religion is about your meaning and purpose and your philosophy of life. Art is what you're giving back to the universe. We may all be created with creativity as one of our fundamental characteristics. And everybody looks at the world slightly differently, and no one paints a painting the same. So anyway, so that's very important for us to be able to give back. So what is our cosmic purpose? That's one question. Science is about cosmic order. So there shouldn't be any conflict with these because they really are, in many ways, they're different ways of looking at the world. Okay, so So anyway, technology is just thrown in here. What's the difference between science and technology? So science is the rules of nature. Technology is the practical use of those ideas. And so there's chemical reactions, one of which has to do with the chemical reaction that can occur maybe during an explosion, okay, the molecules of TNT. And so the thing is that there's a chemical reaction, and then there's using it. How do you use those molecules? Do you use them as gunpowder? That's technology. Do you use them in dynamite? So technology can be helpful or harmful. The scientific knowledge is going to be there, but we can use the atomic reaction to heat our homes, or we can use it to make a bomb, right? So we can use technology, and we're the ones who are responsible for figuring out how to use it. So anyway, we actually do have lots of technology to help solve our current problems. Now we're going to talk about climate change. And one of the things about climate is that we are using too much oil and gas and other fossil fuels and coal to make the energy we need, which is ridiculous because we can get energy in other ways. And we're doing better and better about that. So we're going to talk about that. Pollution comes a lot with that. If we weren't polluting our sky, we probably would not have climate change. Population, we know how to keep from having babies. So we have a lot of technology that can solve problems, but we have to have a society that is going to encourage and accept these changes. So giving up coal, okay, and taking your birth control pills, and educating people. The more education people get, usually the fewer children they end up having, because they have value as something other than just a baby machine. So anyway, so society has to have the will to use the tools of technology. Okay, well, that is actually the end of the prologue. And so we're going to go do a metric system review, but not today. I need to go lie down for a while. So I'll stick around for a few minutes if you have questions, but otherwise you can leave. And so no real office hours today because I'm going to go lie down, rest my back. Okay. So anyway, so class is over. Have a nice day. Stick around if you've got questions.
Thank you.
Okay, thank you.
Bye, have a nice day.
Bye, thanks.
Bye, have a nice day. Hope you feel better.
Oh, thank you. Thanks, Hector. Okay.